Hello, and welcome to the second video in the Chemical Kinetics video series. In this video, we are going to be looking at an example problem. So we'll go ahead and get started. Alright, so this is one of the textbook problems. It's from chapter 13, number 6 at the end of the chapter. And this is just a good practice problem to get used to writing reaction rates. It's also a good problem to do to see how the negative sign that we have in that generic definition of our reactants and how that negative sign is taken care of. So we'll go ahead and get started. When I do these problems, I recommend to always kind of write out that definition for the reaction that you're given. In this case, we're given a reaction of 8 moles of dihydrogen sulfide that reacts with 4 moles of oxygen gas to produce 8 moles of water vapor and 1 mole of octasulfur. This is actually called octasulfur. It's also referred to as cyclooctasulfur. It's found in mushrooms, and it's actually used as a fungal and a bacterial metabolite. So just a fun fact about that one. So we'll go ahead and we'll just write out that rate. Alright, so if you recall, in the previous video, when we're writing a rate reaction definition, or however you would like to refer to it, we're always going to do, I start with the reactants first. They are going to have negative rates. We do negative 1 divided by any stoichiometric coefficient. So in that case, I'm underlining what those would be. There's an invisible 1 in front of that octasulfur. But we're going to write those stoichiometric coefficients in the denominator first. So I'll put an 8 for the dihydrogen sulfide, and then that's multiplied by the change in the concentration of the dihydrogen sulfide divided by the change in time. And that's going to also be equal to negative 1 over 4. Now we're working on the oxygen gas times its change in concentration divided by change in time. Next we'll move to the water vapor. That's going to be positive. Products have a positive rate. It's going to be positive, and you don't have to write the positive sign. I am just for sake of clarity here. And that'll be 1 divided by 8 times the change in concentration over change in time. And that'll be also equal to a positive, and you don't have to put 1 divided by 1, that's a little redundant, so I'm just going to put positive delta S8, just like that. So now we kind of have our definition of the rate reaction, and now we can start filling in this table. We were given the rate that dihydrogen sulfide is being consumed at. It's disappearing or being consumed at a rate of 0.080 molarity per second. And I'm going to just move through each reactant. We have this rate of the reaction that we just wrote out. And since these are all equal to each other, we have this equal sign, all these equal signs, I can actually go ahead and just pick and choose what reactant or product I would like to look at. Since we know the rate at which the dihydrogen sulfide is disappearing, that is this part of the equation, I can pick the rate of disappearance of the oxygen gas, or the rate of appearance of water vapor, or the octasulfur. I can pick it and go in any order. I'm just going to go in the order that these are written in. So I'm going to pick and choose, and I'm going to say negative 1, 8. Go ahead and write this. I'm going to look at this oxygen first, so I'm just going to write what is in this section. We're solving for this chunk right here. And so what we can do to isolate that side, isolate that rate of disappearance, is multiply both sides by the reciprocal of -1/4. And that's just going to be -4. So I'm going to multiply that on both sides of my equation. That will get rid of that -1/4. And now I have isolated that change in concentration divided by change in time of the oxygen. Looking back over onto the left side of the equation, -4 times -1/8 is +1/2. So go ahead and write that. We know what delta dihydrogen sulfide divided by delta T is. That was given to us. So I can just go ahead and multiply that into my equation. That is going to be equal to the rate of the oxygen gas. Now doing this math, and we can just multiply 1/2 times -0.080, or you can divide by 2. This is going to come out to be -0.040 molarity per second. I'll go ahead and put that in. And that is consistent with what we would expect if we just look at, this is a reactant, so having that negative sign there would be expected. We also have a higher quantity of dihydrogen sulfide than we do of the oxygen gas. So we would expect that the dihydrogen sulfide disappears faster. That's if we look at magnitude, the 0.080 versus the 0.040, it is a higher magnitude than this is. So that is expected. This does look correct, and it is correct. So we can go ahead and move on. We can pick and choose how we want to do this. We're really just picking reactants or products, whatever you know something of, you can set that equal to what you don't know. I'm going to just stick with this dihydrogen sulfide because we know what the concentration of that is, what the rate is that was given to us. So I'm just going to keep that side, this little chunk, but I'm next going to set that equal to my water vapor. So this part. Go ahead and write that in. Now we do need to isolate. We're looking exclusively just at that delta water divided by delta T. So I need to isolate that side of the equation. To do that, I can multiply again by the reciprocal of that 1/8. That's just going to be +8. So if I multiply both sides by 8, that'll get rid of that fraction. 8 times -1/8 is -1. And then we do know, again, that change in concentration of the dihydrogen sulfide over time. That's what was given to us, so I can just go ahead and plug that in. That'll be equal to my water vapor. Now, if we did the math here, those negative signs would cancel out, and the change in concentration of the water vapor divided by the change in time is going to equal +0.080 molarity per second. Again, looking through that, that is consistent with what we would expect. It is a product, so we expect products to be positive numbers. And that is why we don't have a negative in the equation for them. We leave them positive. So this makes sense. We also have the same number of moles of both dihydrogen sulfide and water vapor. So we would expect those rates to be the same because of that. So this looks good. And now we can move on to the last product that we have, that octasulfur. I'm going to go ahead and just erase this again. I'm going to use the dihydrogen sulfide one more time. Again, now we're just looking at this last reactant. This one's kind of nice. We don't have any, we have a coefficient in front of it of 1, so we don't have to worry about multiplying by a reciprocal of something. We can actually just go ahead and plug in that given value. And if we do that math, we find that the change in concentration over change in time of the octasulfur is positive 0.010 molarity per second. We only have 1 mole of that versus 8 moles, so we would expect this to be produced at a much slower rate or a smaller rate. It's also a product, so we expect that the rate is positive, which it is. So this is kind of cool to see why and how these all kind of align and work together. The last box that we have to fill is the overall rate of reaction. And it didn't put this in the question, but I'm going to just put in parentheses of the reaction. That's going to be this part right here. Now we can pick any one of these boxes that we have filled in, and we would just plug that into one of these. They're all equal to each other. However, if I'm looking at it, I would have to do a little bit of math, and if I'm doing this on a quiz or exam and I want to get it done, the fastest way I could get it done is just by looking for whichever one has a coefficient of 1. That octasulfur has a coefficient of 1, so I know my rate is going to be the same as the rate of that product or reactant, product in this case. So my rate is going to be the same thing. If I cut and looked at these two pieces exclusively, the rate of the reaction and the octasulfur, I see that they are in fact equal to each other. There's no coefficients, no fractions of any sort, so I can go ahead and fill in this box with that value. And that is how we would do that problem. Again, if you have any questions, please leave a comment. I would be happy to answer any. I'm going to have one more video up of another practice problem, and then we'll move on to writing rate laws and exploring rate laws.